Hello AP Chemistry and welcome to video number 3 where we're going to talk about incorporating some thermochemistry and some equilibrium into our electrochemistry. So if we take a look here, right, this is from from several chapters ago, right, where delta G is equal to negative RT ln K, right? Over here, though, right, is where we tie in our electrochemistry, right, wherein we have this E naught here, so delta G is also equal to negative NFE, right? And there's this third form down here that you can also memorize, though these two will get it done also, whatever floats your boat. You need to know enough of these that given E, you could calculate G or K, right? Couple of notes here. F is Faraday's constant, which is 96,485 coulombs per mole. Okay, it's often written as moles of electrons because of the way we use it, right? Where here, this is moles of electrons, which is why this is generally written as moles of electrons. So anyway, though in your textbook, right, it talks about how this is technically unitless. It's just N, which refers to moles of electrons. The point being that we want delta G to end up as being kilojoules, right, per mole. And again, going back to chapter 5 and 19, right, we interpret it as moles of reaction. However the reaction is written, that's what it corresponds to, okay? So going back over here to Faraday's constant, 96,485 coulombs per mole, going back to what we talked about at the very beginning of the chapter, right, a coulomb is also a joule per volt, right, which is why this is also 96,485 joules per volt times mole, right? Which is why when we take this times my E, which is volts, times my N, which is unitless moles of electrons, right? These cancel and end it with joules per mole, right? So do be mindful in terms of units, right? If the question's asking you for delta G in kilojoules per mole, you need to make sure that when you're done, you do a conversion here, okay? Then that brings us over here, right, where again R, right, going back to lots of things at this point, right? Delta G, right, is an energy, which means that this is the, right, 8.314 joules per mole Kelvin version of R, okay? Okay, so anyway, what that means is that if we know E, we can calculate G and K and talk about the thermodynamic favorability of a process in addition to its equilibrium constant, okay? So here we have a reaction where we're taking nickel and we are going from nickel 2 plus to nickel 0, which means nickel is reduced. And we have chromium hydroxide, which comes over here and becomes the chromate ion, right? And in order to determine that, we would do its oxidation states, right? So this is -1. We have 3 of them, which means it's +3. Over here, this is -2, 8, right? And it'd be +6. That's butter snoring, I'm pretty sure. Anyway, and that is oxidized, which makes sense, right? And then we have these other players in here, right? And that's because most redox reactions actually happen in the presence of acid or base, okay? Which is why when we look at our table of standard reduction potentials, there are lots of other things in here, right? Some of them are just ions and the neutral species, but a lot of these do have, like here we have hydrogens, right? Here we have hydroxides, and so a lot of these are assumed to happen under either acidic or basic conditions. And that's something we sort of skipped over for the sake of time, but note that, right? That's why we have all these other tidbits in here. Okay, so anyway, what is the value of N? Well, that requires that we think about this, or we can look at our equations, right? So we know that from here to here, right, there are 2 chromiums, but each chromium needs an exchange of, right, 3 electrons, right? So chromium is 3 electrons. Nickel is how many? Right, nickel is 2 electrons, and which means that overall we're going to have an exchange of 6 electrons, yes? All right, so that's my value of N. So I'm going to use my data to calculate delta G, right? So delta G naught is equal to negative NFE, okay? So we know that delta G naught is going to equal to negative 6 times 96,485 coulombs per mole times, and by coulombs per mole, we really mean joules per volt mole. And then we have to calculate our E naught value, right? So then, when we go to our table, let's see, we're looking for chromium hydroxide and chromate. So chromium hydroxide and chromate is here, right? chromium hydroxide, chromate. So what do we need to do here? Right, we need to flip this, so it's going to be negative 0.337, right? And then we're looking for nickel 2, so nickel 2, right? So negative 0.28, right? So then what that means, right, we have 7, right, which means we're adding these basically, right, because that's what we do, right? To get their signs right, then we add them. So 8, 9, 10, 11, 3, 4, 5, 6, right? And that's our voltage for our cell, which means that over here, 617, I think that's what we got, right? Okay, so then the whole point being that when we do all this math, right, this is going to be in joules per mole, and what's the sign going to be? Right, the sign is going to be positive, right? Delta G is going to be positive, meaning is this thermodynamically favorable? No, right? Which makes sense because we got a negative value for my E, and if that's negative, right, that means the cell is not going to run spontaneously. It's going to need some outside influence to run. Okay, so then if we want to calculate K, right, delta G equals negative RT ln K, right? So we would take our delta G and plug that in here, and we'd come up with our K value, right? And if this is a negative and we do an e to the negative, we're going to come up with a minuscule value for K, right? Something with a giant negative exponent. Yeah, does that make sense? Meaning the equilibrium lies, right, towards the reactants, meaning it does not progress in the forward direction very much. Yes? All right, fantastic. Next up. So, we have the Nernst equation where we reintroduce Q to the concept of electrochemistry, right? So E, note that there is no not there, right? So this not means at standard conditions, okay? Q, thinking back, right? Q is your instantaneous conditions, whatever it is at an exact moment in time, right? R is our 8.314 joules per mole Kelvin. Temperature, right? N is again your moles, and this is your Faraday's constant again, right? So, what this means is we can calculate E away from standard. So we can calculate E away from standard, okay? So let's look at a reaction as a point of reference. So here we have this reaction, okay, where we're going to oxidize zinc and we're going to reduce nickel. Now let's go ahead and, since we're going to talk about Q and K, let's go ahead and write a K expression, right? K expression is going to be what? Right, it's just going to be Zn2 plus on top of, right, okay, this is a terrible place to put this. I don't know why I did that. Okay, it's going to be Zn2 plus on top of Ni2 plus. Yes, because that's right. We exclude pure solids and pure liquids from our equilibrium expression, which means that this is what we're talking about. Yes? All right. So then, let's talk about, it says EMF of the cell under standard conditions, right? So, I didn't bring that, but if we think about the numbers, it's 0.76, 0.28, so we come out with, so E standard is just going to be the summing of my two half reactions, which comes out to 0.48 volts. Now, something to bear in mind, if we wanted to use the Nernst equation, let's say we were like confused and we weren't sure whether we should use Nernst or just calculate it normally, right? Well, E is equal to E naught minus RT over NF ln Q. So, Q at standard conditions, what does standard mean? Right, standard means that this is 1 molar, this is 1 molar, which means Q is 1, right? Which means that this whole term, right, is void, which means E equals E naught at standard conditions. Yes? All right, moving on to B. So what is the EMF of this cell when nickel is equal to 2 plus and zinc is equal, zinc, you know what I'm saying. And the whole point is that now we're away from standard conditions, which means that now, right, we have to actually think about what that effect is going to be, right? So if we look at E, and this is 0.48 volts minus R times T, unless we're told otherwise, we can assume it's 298. N, how many electrons are transferred here? Right, 2 times 96,000. We're going to estimate 400 coulombs per mole times, right, the ln of Q, which in this case, again, zinc over nickel, right? So zinc is 0.1 over nickel, which is 3. Now, let's talk about what this means in terms of math, right? Your textbook gives a simplification for this because usually we're talking about cells at 298. R is a constant, right? And so is this. So there's actually a simplified version of this where you just memorize one number over n. You're welcome to go look that up in your textbook if you don't want to deal with all this nonsense. So anyway, the key point here though, right, is that I have 0.1 over 3, right, meaning that this is a decimal value, right? If I take the ln of a decimal value, what do I get? Right, a negative number. If I have a negative number here and I minus a negative, what happens? Right, E increases, yes? Meaning that there is a higher voltage that runs through the cell when we skew the concentrations, right, on purpose, right? And that's how a lot of cells are run, where we can skew the concentrations to make sure we get a higher voltage out of them, which can be a favorable thing to do depending on what the point of the cell is, okay? All right, moving on to C, right? So what is the EMF of the cell when we have these other different concentrations? So let's do this, right? E is equal to, again, 0.48, because this is E naught, right? 8.314 joules per mole Kelvin times 298 Kelvin over 2 times that times the ln of, so zinc is 0.9 over 0.2, right? Meaning that now, what kind of value is this? Right, it's the ln of a number greater than 1, which means that this number is going to be, right, positive, which means that we are actually going to subtract from here, which means that E is going to go down, right? So when we skew these in the other direction, my cell voltage goes down. Now, every time you're asked to explain one of these, it should always go back to Nernst, okay? Every time we have concentrations away from standard conditions, your explanation needs to go back to the Nernst equation. But in order to double check yourself, right, you can double check yourself using Le Chatelier's principle, okay? Le Chatelier's doesn't strictly apply here because we're not talking about a cell at equilibrium, right? We are talking about a cell that's away from equilibrium, which is why Le Chat doesn't work, okay? But we can use it to kind of double check our logic. So if we think about here, right, when we have zinc as being 0.1, zinc being my product, if my product value is small, it makes sense that my reaction is going to shift to make more product, meaning increase voltage, right? Here, when my product is higher than my reactant, right, it sort of logically makes sense that my cell is not going to move as forward, or not going to move forward as much, right, because we already have a surplus of product, yeah? So that's just a kind of way to mentally double check yourself. That should not be the explanation that you use. Now that we have Nernst out and we're talking about it, right, let's think about what happens over the course of time, right? So this starts off as 1 molar, right, because we have 1 molar on top, 1 molar on bottom. What happens as time goes on? Right. So this is my zinc, this is my nickel, and if we look at the reaction, what's going to happen as time goes on is the zinc is going to increase, right? And the nickel is going to decrease, right? Which means that eventually, what's going to happen? Right, this number is going to get bigger and bigger, right? And we're going to end up in this scenario here, which means that inevitably, what happens to all cells? Right, eventually all cells end up at a 0 voltage, yes? Because as we deplete our sources of our ions, the cell ceases to run eventually, right? Which is why, if we think about what that means, when a cell reaches equilibrium, what are some of the ways we describe equilibrium? Right? It's the rate of the forward equals the rate of the reverse, no net change because those rates are equal, right? Which means that if there's no net change, right, that means we are sending as many electrons forward as we are sending backwards, which means that the measured voltage becomes 0, yeah? All right, finally, last up for concentration cells. So here we have a concentration cell, right? It's constructed with 2 zinc solid, zinc 2 plus half cells, right? Which means that we have the concept of our cells again, right? Where both of them have zinc. Okay, both of them have zinc solid, and both of them have zinc 2 plus floating around. But like we just said, if we skew the concentrations right, we can make the voltage be favorable. Now, let's just talk for a second. If we have zinc and zinc 2 plus in both of these cells, what is my E naught? Right, E naught equals 0, right? Because we have the oxidation of zinc in one direction, the reduction of zinc in the other, which means that if I sum those, right, I'm going to get 0 as my E naught. If you're not sure, go look through your book and make sure you are sure. All right, so let's talk about which half cell is the anode, right? Anode means oxidation. I have no idea. Oxidation. right? Which means that we are looking for the cell where Zn is going to go from Zn solid, right, to Zn2 plus 2 electrons, right? So let's think about which cell would be logical for that, all right? One cell has 1.35 molar zinc, and the other cell has 3.75 times 10 to the negative fourth molar zinc, right? So, thinking about my equilibriums, thinking about everything we know, which one's going to be the anode, the place where oxidation occurs, the place where this occurs? Right, this one is the anode, because the anode is the place where we're going to make zinc ions, right? That means here, where we have the lesser concentration of zinc ions, that's where we're going to make more ions, meaning that this half cell is our anode, and this half cell then becomes our cathode. Yes? All right. And then, so the EMF of the cell, right, so E naught is 0, but the EMF of the overall cell, right, would be E equals 0 minus RT over N. What's N in this case? All right, 2 electrons, 2 times 6,500 times the ln of products over reactants, right? So let's think about what that means. Here, zinc product, right? And let's think about what's happening, right? So my electrons are starting here, right? And they're going over here, right? Which means that this part is getting depleted, or this part is being replenished in terms of ions, right? We are making ions here. If we are making these ions, that's my product set of ions, right? So 3.75, E negative 4 up top, right? And my 1.35 on the bottom, because this set of ions is going to get depleted. Yes? Right? We are making these ions, which means this is a product. We are using these ions, which means that's a reactant. Yes? And we would solve for this and we'd come up with an E value, right? And again, we have a number here that's going to be a decimal value, which means a negative value for the ln of that, which means we're going to come up with an overall positive value for E. Yes? All right. Thank you for listening. Be good, and I'll see you soon. Bye.